Okay, good afternoon. My name is Suren Singh. I'm actually going to be presenting a flash seminar here on the real-time uncertainty at millimeter wave. Primarily, I'm going to be looking at how we actually do uncertainty measurements currently and what the real-time uncertainty calculator does for you. It's a set of software that's on our PNAX that allows you to do real-time S-parameter uncertainties. So if you looked at how people do uncertainty today, what they do is do a raw measurement. If you currently look at how you do uncertainties, what you would do is do a raw measurement. Once you've done that, you take your calibration, you do your calibration on that system, and I'm talking purely about S parameters here on a vector network analyzer. And then you get your corrected measurement. Now you've got that corrected measurement. How do you determine what the uncertainty of that corrected measurement looks like? Well, what you would traditionally do is either look at a data sheet, run our uncertainty calculator, and then you would look at the uncertainties as you see at the bottom of that screen, and then determine that to be your uncertainty of your measurement. And that's how you traditionally do it. That is not real time, it's not dynamic, and you want to be able to do something that's real time and dynamic. So the new method of the real-time uncertainty calculator works differently. What it will do is during the measurement of the device, we look at the noise of that measurement. We also look at the calibration standards and their uncertainty. And also we look at the repeatability of that measurement plane. So in other words, if you have a 1 millimeter connector or a 3.5 connector, we look at the repeatability of that. All of that feeds into the final answer, which is your device under test. And at that point, we compute the uncertainty. So you must be wondering how we do that, okay? So let me show you a little bit of what the background looks like. We actually look at it as a different model. The traditional network analyzer model used a flow graph technique of looking at the reflection tracking, directivity, and source match, and load match. What we look at here is a wave model. The network analyzer is either sourcing, a port is either sourcing a signal or it's receiving a signal, which means that it can be either represented as these equations, and I'm not going to look at those equations, but the nice thing about those equations, which I don't show here, but if you go micro apps, you will understand a little bit more. It allows us to actually derive a linear equation which we can then determine the uncertainty of. And that's primarily what you want to be able to do. So with the new model, we can actually add the noise uncertainty, and I'll look at each one of those in a minute. So first, let's look at the noise. So the noise can be represented either as trace noise during the measurement, and that equation represents that, or the noise floor. If you can characterize the trace noise and noise floor of your measurement system, you then can derive the uncertainty of that measurement for the noise, okay? And that's a high-level set of equations. I could go deeper, but that's showing your uncertainty for your noise. And the way we measure that, this is showing the actual interface. You determine the noise by measuring a load, and then you measure a flash short or a short condition. So you got your trace noise and your noise floor. So you got that set of data, right? The next set of data you need to get is your calibration standard uncertainty. How do you determine calibration uncertainty? Well, the way to do that is you either specify it mechanically, and you look at the tolerances for that mechanical standard, and you present that as either a random variation of it using a Monte Carlo analysis, and determining what your uncertainties are for each of the variations of those standards. That standard can then be used with its data and uncertainty. This is an example of 120 gigahertz. I guess it's a load or offset short, and you're looking at the uncertainty bars around that. So that's the type of data that we feed into this software. So we got the noise, we got the uncertainty of the calibration kit, the repeatability of the connector is the next thing we look at. So we look at the repeatability. We basically model it as a two-port structure. In other words, it has an input and a transmission, and a reflection and transmission characteristics. The reflection and transmission characteristics are represented by this set of equations, and basically you can derive the uncertainty based on that. Once you've determined that, you could by using a set of shorts and rotating the phase and a set of loads, you can get the reflection and the transmission characteristics. So once you determine that for the connector, you now have all three of those parameters that you need. Now I'm going to switch gears a little bit about the uncertainty. If you're looking at it at millimeter wave frequencies, there's a couple of things you need to be aware of. Firstly, the connector that you're using has to be a traceable connector. In other words, it has to follow a standard. Our connector on the Keysight implementation is the IEEE 287 standard that's implemented and uses traceable calibration standards for it. So it allows you to get a broadband calibration at that port. Okay? This is the other thing that when you're looking at a millimeter wave solution, it is a distributed network analyzer, which means that most of the actual network analysis happens in the modules. And by happening in the module, you need to make sure that those are stable. If you look at the system we have over here, it actually has a single cable. That single cable actually has a LO, RF, and IF. If I move the whole thing, they all move together, which means that the mechanical stability is improved on a system like that. The other thing is the actual thermal stability. And here you're looking at transmission stability through a cable, and that's 24 hours at 25 degrees. And you can see what the stability looks like. So from a millimeter perspective, to ensure your uncertainties are good, you've got to make sure you have good implementation of the hardware. The other thing is, in terms of performance of the system, you want to make sure that you maintain the system. In other words, even though you buy the system today, you need to, we recommend on an annual basis, have it calibrated. Because these connectors are pretty fragile. I mean, not fragile, but they always need to look at the pin depth. You want to make sure that their repeatability is within your uncertainty, and so that you can have it calibrated annually. What I'm showing here is several measurements of different pin depths, and that's a 3.5 millimeter connector over several services. So having the system serviced is a key part of also maintaining good uncertainty at millimeter wave. This is the final slide of this presentation, but it basically shows you the actual uncertainty software at its best. So what you're seeing here is a set of uncertainty bars across up to 125 gigahertz. That's looking at a 10 centimeter line. That's your S21, S12 uncertainty. One of the other things is we can represent the actual match as a polar graph and actual distribution of that over frequency. Now remember, all of this is happening real time while we're measuring the device. So you don't have to go back and figure out the uncertainty. You can also look at the uncertainty in terms of the coverage factor, 1, 2, and 3 sigma. So it allows you to do that. You can look at the max uncertainty or the minimum uncertainty and apply different uncertainties to the measurement. For instance, if you wanted to look at just the noise, you can uncheck the calibration and the repeatability and look at the noise effect. If you wanted to look at just the calibration kit effect, you could do that, and you'll see that these bars will change. Okay, and that's basically what I had. These are references to the actual technology behind the software, and you can see those two. The other thing that we did with the real-time uncertainty, the actual method of calculation was validated using National Metrology Institute software from METAS and from NIST, which means that the data that you're seeing and the software that you're applying is actually traceable. I'd like to thank you for your attention.